So, last class we ended up talking about the shapes of these atomic orbitals. Can you hear me okay, or am I talking too quietly? Okay. So, we're talking about the shapes of these atomic orbitals atomic orbitals around the atom. We talked about the P shape, P orbitals being dumbbell shaped. We talked about our d orbitals, these being the shapes of the d orbitals and the corresponding names. And I wouldn't expect us to be really responsible for the names of these orbitals. The thing that we do want to recognize is that when somebody refers to the name of an orbital, it's usually associated with the axes that that orbital is around or related to, right? So now we're going to talk about a concept called effective nuclear charge, all right, or shielding, and the size of a given atom, okay? Now, the size of an atom is related to the electrons that are farthest away from the nucleus, okay? Kind of like if I were to draw a fan with three different blades, all right? If this thing is spinning around, all right, then in reality it's a fan with three blades, but essentially it looks like a disc. And anywhere where I would put my finger, I would get hit by the disc. I would touch the fan, right? So the size of the fan would really relate to the size of one of those blades, right? Well, the same principle is taken into account when we're talking about the size of an atom, right? Because although we've been kind of drawing atoms on these axes, which is fine, in general, an atom by itself will be tumbling, spinning around. And so if I were to kind of see this thing tumbling around, what I would really see is basically a spherical entity, right, spinning around. And if I were to reach my finger in and touch it, the size would be governed by basically, right, this distance here would be basically governed by the size of the orbital, okay? So the furthest electron, the electron that's farthest away, kind of governs the size of the atom. Now, if we use kind of our orbital model to think about this, then electrons which are closer to the atoms, or closer to the nucleus, electrons that are closer to the nucleus will be shielded, we say, shielded from the nucleus by other electrons that are kind of in the way, all right? That shielding, also the corresponding n value, remember n equals 1, 2, 3, right? And we said that the higher the n value, the higher the energy, meaning an electron that is high in energy might be stabilized by a different nuclei somehow, right? So a high n value, n equals 4, let's say, for example, out here, whoops, high n value, a little bit of shielding, right, results in that electron kind of straying farther from the nucleus, all right, and resulting in a bigger atom, okay? So the effective nuclear charge is how much positive charge this electron is actually kind of feeling. Now, why is it not feeling very much? Because it's far away and there's other electrons in the way. Its distance, that's its n value, and then shielding is these other electrons that are kind of in the way. And so the result is the size of atoms, the size of atoms follows these trends here as shown. If we look at lithium and move down to sodium, potassium, rubidium, and so forth, we shouldn't necessarily be surprised that sodium is larger than lithium, Let's write some electron configurations here for lithium and for, where are we at? Lithium and for sodium. Lithium is 1s2, 2s1. Is everybody okay with that? Can somebody help me with sodium? Emma Lee, can you help me with sodium? If lithium is 1s2, 2s2, or 2s1, what's sodium, Emma Lee? What's its electron configuration?
One second, sorry.
Electron configuration for sodium.
I'm not sure.
All right. James Oliver, you want to give it a shot? Electron configuration for sodium. What do we got here?
1s2, 2s2, 2p, right?
Yeah, 2p, good.
2p6 and then 3s1.
2p6 and then 3s1. So now again, how we did that, right? Maybe I bring up a periodic table down here so we can look at it. This is our first row, 1s2, our second row, 2s2, and then 2p6 if we're going to sodium, and then that's 3s1. For lithium, 1s2, and then 2s1. We stop right there. So taking these electron configurations into mind and looking at the size of sodium compared to lithium, right? Shouldn't be surprising to us because we have a third shell right there, right? We have the first shell, 1s, the second shell, 2s, and in this case 2p, and then we have the 3s. So because sodium has the 3s, we get an increase in the size. Potassium, it would have the 3s, the 3p's, and then the potassium would be 4s1, right? So as you have more shells, then it's not a surprise that the atom is larger. Okay? Now, why is it that, for example, when we move to the right along these shells, the atom actually decreases in size? So why is beryllium smaller than lithium? Well, let's look at the electron configuration for lithium and compare it to that of beryllium, right? Beryllium, 1s2, 2s2, right? So you might say, well, it's clear that those two electron configurations wouldn't result in beryllium being much larger because that second electron is going into the same orbital. It's just one has one electron and one has a second electron, right? But why would it actually get smaller? Why would beryllium actually get smaller? Well, that's because beryllium has another proton. So lithium has 3 protons, but beryllium has a 4th proton. So there is another electron, but because that electron is going into the exact same orbital as the last electron that lithium had, that extra proton allows the size of the resulting atom, the distance of the 2s electrons here, to actually be closer. And the model that I like to use for this is to imagine an atom represented as a family, all right, with the adults, the parents as the nucleus, and then the children kind of wandering around the parents as they move through maybe a public space like the mall or something, right? Okay, so here we have our nucleus of parents, and then we have the electrons moving around there. Well, if this child, the electron, moves too far away, the nucleus says, hey, come back here, don't touch that, stay away from those, don't bother your sister, that sort of thing, right? And so those nuclei are keeping the resulting electrons from roaming too far. All right. If you add an additional nucleon, an additional proton specifically, right, then that allows, if I have another proton in there, then it allows more kind of parental figures to prevent the kids from roaming too far away. All right. So we use this model for a handful of things here at the end of this chapter. But essentially what we're seeing here is that the size of the atom relates to the number of protons that there are, and also how the electrons are being added to their orbitals or their subshells based on the electron configuration. All right, so for example, if we look at boron 86 going to neon, well, let's do aluminum to argon because it's a little bit easier to see on this image. Aluminum 143, and the units for the size here, the radius, is picometers. Aluminum's 143 picometers, and as we move to the right, argon goes all the way down to 94. So why is that? Why is it that when we're adding more electrons, the actual size of the atom is not increasing? So let's answer that question first. Why is the size not increasing? And then second, we'll say, why is the size decreasing? So, Catherine, can you tell us why the size is not increasing as we move from aluminum to argon?
Because there are more protons, so the electrons are closer to the nucleus?
Well, that's actually the reason why the size is decreasing. That's right. That's fine. That's fine. And the reason why the size isn't increasing is because the electrons are all being added to the same subshell. And what subshell is that, Catherine? What subshell is our aluminum to argon the electrons being added to?
2p?
Almost.
Oh, 3p.
Yeah, 3p. We're in the third row here. Very good. So if we kind of try to draw ourselves a 3p orbital here, 3 subshell, 3p subshell, right? The first electron goes into that 3p. Let me make some space here. First electron goes into the 3p, right? We can kind of shade in one of these orbitals. Second electron goes into the 3p as well. Again, no reason that this should be any larger. Third electron goes into a 3p. Fourth electron goes in, pairs up with another one here, right? But fourth, fifth, and sixth, no reason that the size of the atom should increase because we're just going into the same subshell. In fact, the decrease occurs because every time a new proton is added, the electrons get closer and closer. All right, very good. So based on that, Katie, what do you think is larger, an atom of hydrogen or an atom of helium? What do you think is larger, Katie?
Hydrogen?
Hydrogen, that's right. Hydrogen is larger. So helium is smaller because there's an additional proton pulling that electron that's in the 1s, right? It's still both hydrogen and helium's electron are in the 1s, but helium has one extra proton pulling it smaller. Very good. So everybody take a look at this one. We won't break into groups, but you can take a look at this one and tell me what you think. Which one has the smaller, or sorry, which one of these comparisons is correct? Look at it for about 20 seconds and then Landon will tell us. And the ones that aren't correct, have in your mind ready to explain why they're not correct. Okay, Landon, what do you think? Which one of these is correct? Nikki, do you want to help him out? Which one do you think is correct?
I think B is correct.
B is correct. So you are saying that an oxygen atom is larger than the... Oh, we didn't really talk about this yet, did we? Sorry, we jumped the gun on this. Let's go back to this this slide here and look at this. So if we have this example, where did I put my kids walking through the mall, right? If we have this example where we have some parents and some kids walking around in the mall, right? Then, as you would suspect, if you take this situation and add another child, if you add another child, what do you guys think? Would that increase or decrease the kind of the swath, the space that that family would take as they walk through the mall, Nikki?
It would increase.
Increase, that's right. Another child increases it because now it's harder for the parents to kind of manage the children, right? And that's the way it is for my family, right? If I have my 6 kids walking around, you know, we're a pretty big bunch. But if you bring an extra kid or 2, friends, right, then the kids become a little unruly and they take up more space. All right? Very good. So the analogy is then comparable to something like X, where this atom has a certain size, compared to X with 2 extra electrons. Which one do you think would be larger, Samantha? X or X with 2 extra electrons?
X with 2 extra electrons.
That's right. The extra electrons make it larger. Now, a different scenario. Maybe I have a family, right, with some parents, number of children doing their thing, right? But then let's say a couple of them had to stay home. All right, so here's X, and then X with a positive 2 charge because 2 of those electrons are now missing. How would the size of that atom change? Which one would be larger? Which one of these would be larger, X or X where 2 kids had to stay home? Kim, Taiwan, what do you think? Which one would be larger, the X or the ion?
So it's X.
That's right. X will be larger than this ion because in this ion we've lost 2 electrons. And if there's fewer electrons, it's easier for those protons to pull those electrons in. All right, Nicole, let's go back to this question now. See if that helps. Give you a shot at redemption here.
So then it would be
A, that's right. We see that magnesium atom is going to be larger than its ion, right? It's not always that atoms are larger than ions. It's atoms will be larger than cations.
But if you're looking at, so you have the oxygen, and then if you did like the -2, it would go to neon. But neon would be smaller than oxygen, right? Or is that not how it works?
Neon smaller than oxygen. So let's bring up our periodic table and take a look at where we're at here. So neon and oxygen, why would we say that neon would be smaller?
Well, because it has more protons.
That's right. And all the electrons that are added in from oxygen to neon are going in the same 2p subshell, right?
Yeah.
Now, what would you say about neon and argon, Nicole?
Argon would be bigger because it's in a different N.
That's right. That's right. Different N value, 3rd shell. Very good. So, you know.
But I'm because it said the O minus or 2 minus. So would you not do like, because you know, if you had the 2 or a -2 charge in the O, it would go to neon? Or is that not what it's talking about here?
Well, it's not saying that we've increased the number of protons. You're right. It's saying we have the same number of protons, oxygen atom and oxygen 2 minus, both have the same number of protons, but now this species over here has 2 extra electrons. So that would be larger if it had 2 extra electrons.
Okay.
Does that make sense?
Yeah.
All right. Excellent. So let's see if we can give Landon a chance to answer a problem for us. What do you think, Landon? What's bigger? Bromine or its ion? Landon, what's bigger, bromine or its ion?
I would say bromine.
Bromine is bigger than its ion?
Well, wouldn't its ion have a -1 since it's trying to become a noble gas?
That's right. That's right. Bromine would have a -1. So let's compare that then. We have bromine. How many protons does bromine have?
35.
35. So here's the nucleus with 35 protons. All right. And then 35 electrons. So 35 protons, 35 electrons. All right. And we'll say that looks like that. Okay. This is our bromine. Now, bromine that has an extra electron, because that's the ion that it likes to form. How many protons?
Sorry. Be 36.
No.
Or,
Protons.
sorry, 35.
Maybe I didn't say that right. Protons, 35 protons, that's right. Now, how many electrons in this species?
36.
36 electrons. So, would you expect the size of this thing here to be larger or smaller?
Okay, so the ion would be larger because it has one extra electron.
That's right. It's going to have an increased size because same number of protons, but an extra electron now.
Got it.
So, how about this one then, Landon? What's larger, strontium or its ion? Strontium's larger? Is that what the answer was, or are you thinking about it still?
Yes, I'm still thinking about it.
Okay,
I'm
what's
looking for
larger, strontium or its ion?
I believe strontium.
Yeah, that's right. In the cationic case, right, these are our scenarios where we form cations, right? These are our anions. In the cationic case, the cations are going to be smaller because they're losing electrons, right? So we got strontium here, 38 protons, 38 electrons. Strontium, its ion is a +2, still 38 protons, but only 36 electrons. So whatever this is going to be smaller because 2 electrons fewer, and the protons can bring them in tighter. Okay, good. So positive ions are always smaller than atoms, while the negative ions are always larger than their atoms that they were formed from. Okay, excellent. And again, our information from our electron configuration allows us to kind of visualize that and understand that. Now, we're going to introduce another property that elements have, and it's called ionization energy. Ionization energy is the energy associated with making an atom a cation. So here it is, this energy here, or this atom here, becoming a cation, and the electron is released, and the energy associated with having to do that process is called the ionization energy. I don't like the term ionization energy because there's not just one kind of ion. It's not just a positive ion. So whenever I hear ionization energy, my head always thinks, are you talking about forming a cation or forming an anion, right? Because those aren't the same. But again, this comes from a long time ago when that sort of thing wasn't heavily kind of differentiated. So they should call this cationization energy. So when anybody talks about ionization energy, you'll have to remember that they're always talking about cationization energy. Now, using that same model, all right, a family model where you have some adult figures and some children, right, in your atom, what do you think? Will the energy required, or will it require energy to do this process, or will it release energy to remove an electron from its family? Let's see, whose turn is it? We were at, I think we're at the top again. Emily, what do you think? Is it going to require energy to remove an electron from an atom, or is it going to release energy when an electron is removed from an atom? What do you think?
Would it require energy?
Okay, that's right. That's right. And the way we can think about that is, again, if I have some parents here, right, and then the number of electrons that they have are there. If you're going to take an electron away, if you're going to take a child away, the parents aren't going to like that, right? They're going to be upset about that, and so that's going to increase the energy of the household. So it's going to require energy to remove an electron. So when you see a list of energies, ionization energies, they won't necessarily be, well, I mean, whenever you see any list of energies, you have to kind of think, is this energy exothermic or endothermic in terms of is this energy that's released or required? Because a list of energies might not just say this is how much energy is required or released. It'll just show you a list of energies, but you have to kind of know that it does require energy to remove an electron. With that in mind, James Oliver, what do you think? Do you think it would take more energy to remove a second electron, which we call successive ionization energies? Do you think it would take more energy to remove that second electron, or would it take less energy than the first one? James? You there, James? What do you think? More energy or less energy? I think it would take more. That's right. To remove that second electron, it's going to take more energy. Very good. And that's the way it is for ionization energies. The first one, removing a child from a family, requires some energy. If you remove a second one, it requires even more. The third one, even more, and so on. We call these successive ionization energies. All right, and we're going to see some patterns that relate here for these ionization energies that relate to our electron configurations and our orbital diagrams. Okay. If we look at a periodic table and we kind of see the amount of energy required to remove an electron from an atom, we see it kind of looks like it's bouncing all over the place. But in general, as you move to the right, the energy increases, and as you move up, the energy increases. So let's look at this trend. Radon to helium. Radon to helium. So why do you think helium, the helium family, which is the nucleus with its electrons, why do you think it's harder to remove an electron from helium than it is from radon, Catherine?
There are less electrons?
That's right. If you have 2 protons and 2 kids, right, it's going to be hard to remove one of those kids. But if you have 86 kids, you probably wouldn't miss it as much. I mean, it's still your kid. Yeah, sure. But 86 is a lot of kids, right? So it gets harder to remove an electron from atoms that have fewer electrons. Very good. Now, what about, and that's a general trend moving up our periodic table. But if you see here, as you move to the right within shells, within subshells, so for example, aluminum to argon, right? It's requiring more energy to remove an electron from argon than it is from aluminum, all right? Or if we look at boron, carbon, nitrogen, oxygen, fluorine, neon, right? We see this weird kind of bump in that staircase. So let's see if we can use our orbital diagram to understand why these energies differ the way that they do. So in neon, let's see, Katie, it's your turn to answer this question, so pay attention. In neon, if we're removing an electron, or for all of these, for boron to neon, when we're removing an electron, which subshell are we removing an electron from, Katie? Which subshell is that? Boron to neon.
That's 2p.
That's right, 2p. So the 2p subshell is going to look like this. And if I draw the 2p configuration, for example, for neon, I have how many electrons in the 2p for neon, Katie?
6.
6. 1, 2, 3, 4, 5, 6. Now, if I compare that to something like fluorine, I only have 5, right? 1, 2, 3, 4, 5. Now, which one of these scenarios do you think it would be harder to remove an electron from? Well, we know the answer. We have the chart in front of us. It takes more energy to remove an electron from neon than fluorine. And now our answer has to sound something like this. It takes more energy to remove an electron from neon because when you remove an electron from neon, you disturb a fully filled subshell. But when you take an electron from fluorine, you already have a disturbed subshell, so it's not as much energy to remove an electron from fluorine. Okay? So, Landon, it looks like it's your turn again. Why don't we try to answer the same question in terms of why is there a discrepancy between nitrogen and oxygen in terms of energy necessary to remove an electron? Why is it easier to remove an electron from oxygen than it is from nitrogen? And let's use our orbital diagram to answer that question. Any ideas, Landon? Why is it easier to remove an electron from oxygen than it is from neon? Or sorry, nitrogen.
It's easier to take one from oxygen because you're only dealing with 2 unpaired, what those be called, orbitals.
Uh-huh.
Yeah. And then with nitrogen, you're dealing with all of them since they're all unpaired.
Okay, very good. So here we have nitrogen full. How many more electrons do I need to fill up oxygen?
1.
One. That's right. So nitrogen, when I remove an electron, what am I disturbing?
The whole block.
Yeah, you're disturbing a perfectly half-filled subshell. Whereas here,
Yeah.
when you remove one from oxygen, you're actually doing what in terms of stability?
In terms of stability, you're
I'm creating what?
You're creating a balance.
Yeah,
I
I'm
guess.
creating a perfectly half-filled subshell, right?
Yeah. Mm-hmm.
Whereas here, if I want to remove this electron, I'm destroying that half-filled subshell. Okay, so
Got it.
that's why we see this kind of trend among all of these. But then when you get down here, the trend becomes really less pronounced. Let's see. Why do you think that's probably the case, Nikki? That down here, our trend becomes so much less pronounced than up here.
Was that asked to me?
Yeah, sorry, Nikki.
Oh, can you repeat that question?
Sure. Why? So did you follow why we decided that it was easier to remove an electron from oxygen than nitrogen? Did you follow that part?
Yeah.
Okay. And we see that same scenario like between phosphorus and sulfur, but it becomes less pronounced as we get down here. And why do you think that when you come down to the 5th energy level, it's less pronounced now? The difference between antimony and tellurium is minimal at best.
Because they have more electrons?
That's right. Between here and the nucleus, we have all of these d electrons, these other s electrons, a whole nother set of p, a whole nother set of d, some more s, right? So you have so many more electrons that the energy difference becomes smaller and smaller in terms of to remove an electron from that atom. Okay, very good. So, in terms of successive ionization energies, successive ionization energies. Like we said, here's fluorine, and this is how much energy it takes there to remove an electron from fluorine, right? Takes some energy. The second one takes more energy. The third one more, and so forth, and you see an increase as it takes more and more energy to remove that successive electron. However, there comes a point where there's a huge jump, right? Oxygen, same thing, an increase in the amount of energy, but then there comes a point where there's a huge jump, all right? Can we use our electron configuration to explain why, for example, let's use carbon, it takes an increase in amount of energy to remove the first, second, third, and fourth electron, but why is there such a huge jump between the fourth and the fifth for carbon? All right, can we use our electron configuration, Samantha, to explain, can we use our electron configuration to explain why there's such a huge jump between the fourth and the fifth electron in carbon?
Would those be the electrons in the S shell?
Okay, very good. So we have carbon. Electron configuration is 1s2, 2s2, 2p what for carbon? Samantha?
2p4?
I think it's just 2, isn't it, for carbon?
Right.
Right, okay, good. So we got 1s2, 2s2, 2p2, and apparently I can remove 1, 2, 3, 4 electrons relatively easy. It takes energy, but not compared to the fifth electron, because that fifth electron, where is it coming from?
So 1s2?
Right, which is our, if we draw a noble gas electron configuration, is the noble gas core, right? So it takes energy to remove electrons, but when you want to remove an electron from the noble gas core, that's going to require a lot more energy. All right? So for oxygen, 1, 2, 3, 4, 5, 6 electrons come relatively easy, but the seventh reaches into the noble gas core. Is that true? Our electron configuration for oxygen is helium, 2s2, helium, 2s2, 2p4 for oxygen, right? So we have 6 electrons that can be removed relatively easy, but then reaching into the noble gas core is hard. Let's see, that was Samantha, correct? So Kim, Taewan, how many, or what do we call these electrons? The electrons that are outside the noble gas core with the largest N value. Do you remember what we call those electrons?
Sorry, I don't know.
Okay. We call them the valence electrons. Remember that? They have the highest N value. They're outside the noble gas core, so we call them the valence electrons. So valence electrons will generally be removed much easier than the noble gas, any electrons with a noble gas core. Okay, very good. So that's successive ionization energies. This here is just our irregularities in the ionization trend that we talked about when we were looking at this figure here. All right, and we talked about why it's easier to remove an electron from oxygen than it is from nitrogen. And we showed that the 2p electrons in nitrogen create a perfectly half-filled subshell. So to remove an electron, it requires more energy than it would for oxygen, where we have an extra electron, and we remove that one, and it results in a completely half-filled subshell. Okay. The opposite of ionization energy is something we call electron affinity. Electron affinity. And the word affinity might be a new word. I don't know if you guys have heard it used, but an affinity means kind of an attraction or how much desire somebody might have. So somebody would say, I have a strong affinity for chocolate, right? Meaning I want to eat a lot of chocolate, right? So affinity means in terms of electron affinity, it's how much pull an atom has on a given electron. And specifically, when we're talking about electron affinity energies, we're talking about the energy associated with an atom gaining an electron. Okay? Now, we said that if I have a nucleus with electrons around it, it will always require energy to remove an electron. Kind of like a family with some kids around, it'll always require energy to remove an electron. Remove the first one, remove the second one, it always requires energy. Okay? What do you think, Emily? If I had a family here, right, here's the family, some parents, and then the electrons, what do you think? Would it require or release energy to add an electron to that family? Or to add a child to the family? There's no right or wrong, Emily. What do you think?
Release energy?
That's right. Everybody will take one child, right? Some orphan child, yeah, we'll take it. It's okay. And so it actually, when an atom takes in an electron, it will release energy. Okay? Now, that's one, right? Everybody feels sorry for one orphan. But two, the first electron to come in will release energy, but the second electron to come in, that one will require. Yeah, you'll take the second child, but I need a little help then. Something, it's going to destabilize our system, right? First electron will release energy, but the second and third and so forth, moving on, will require energy. Okay? So electron affinity energies then will come with either a negative sign or a positive sign. What does this negative sign mean here? Where are we at? James Oliver. What does this negative sign mean? Not that it's gaining energy, but that the system is losing energy, right? Remember how we said the change in energy, or the change in whatever, will be energy final minus energy initial. So if the result of final minus the initial is a negative value, negative 141, then that means the initial must have been higher than the final in terms of energy. Therefore, to get a negative value, we must have released energy if final minus initial equals a negative value. Okay? So, the negative there is showing that energy is being released, just like before. Delta H, negative value, that energy is being released to the surroundings. Same thing here. An atom is releasing energy when it takes an electron. However, the second electron, that positive sign, what does that positive sign mean, Catherine?
Requires energy.
It requires energy. For an atom of oxygen in this specific case to take a second electron, it requires an energy. And see how much energy more it requires, right? So we're releasing 141 kilojoules per mole here, but it requires 844 to take that second one. So the sum of those two for an atom of oxygen to take 2 electrons actually requires energy overall, right? The sum of those two. Okay? So if we look at the trends in electron affinity, how much energy is released, all right, because like we said, it releases energy for an atom to take electrons, okay? If we look at this trend, it increases as we go up or to the right, okay? So let's look at that case. Let's see, Katie, If I give an electron to cesium, is that going to require energy or release energy, Katie? If I give an electron to cesium, will that require or release energy?
Release energy.
It'll release energy. That's right. If I give an electron to cesium, it will release energy. And Landon, if I give an electron to sodium, will that require or release energy?
I'd say release energy.
That's right. Giving an electron to sodium will release energy, just like if I give an electron to cesium, it will release energy. But Landon, which will release more? If I give an electron to sodium, will that release more or less energy compared to giving an electron to cesium?
I think giving one to sodium would release more energy.
That's right. So that's what with this figure here is showing us, that the energy associated with gaining an electron increases as you move up, right? An electron or an extra child, you could think of it, to a family that has 11 kids would be more influential than an extra child that went to a family that had 55 kids, all right? So as you move up here, the energy associated with getting an electron affinity, increases. And as we move to the right, the energy associated with adding an electron also increases in energy. Okay, so that is about all we have for this section, for this chapter. That means that the next chapter that we have, chapter 9, is what we'll start on Monday. Does anybody have any questions about what we went over today? So we'll start chapter 9 on Monday, and we will, I'll try to set up a practice exam. We're not going to have a full exam for chapters 1 through 8. We'll set up a practice exam. I still haven't figured out the best way that we're going to do the proctoring for the exam. I think right now it sounds like we're going to use something called Proctorio. Have any of you guys dealt with classes that have used Proctorio before? Let's see. Katie, are you replying yes to that question? It looks like it. So do you want to tell us about how Proctorio works? I've never used it before.
Basically, you just have to download it like an extension, and then it records you while you take the exam and make sure you're not cheating.